As we said at the beginning, we are basically dealing with three systems. We start with the shallow water equation for the ocean, and we're going to look at the shallow water system for the ocean and the atmosphere, and then we're going to add vertical structure to the atmosphere. Starting with the upper ocean, then we are looking for the ocean equivalent of the equation we just wrote, d squared v dy squared plus py dv dy plus qyv, where we started with our perturbation linearized equations. We transformed them into just a function of v because the coefficients were independent of x and t, and then that gave us the wave equation. The governing equations for the upper ocean, then vertical velocity of the system, as we did before, is eliminated by vertically integrating the equations, and w is 0 at the top of the surface, and the ocean is now considered as the upper layer, which is active, and a deep ocean layer, which is basically quiescent. So then our system is just the upper layer and the interface between the active layer and the deep quiescent layer. So we will be looking at W here as dH prime dt, where H is the interface of the two layers. So H prime here is the deviation of the depth of the upper layer, which is important for the upper layer in terms of divergences and convergences, but the deeper layer is so deep that it's not going to bother about it because it cannot have motions. Vertically integrated velocity components in the upper layers are u prime and v prime, and the low level is assumed to be motionless, so the interface variability is going to be too small compared to its total depth. In other words, this is the deep layer, so h prime obviously has to be much less than h prime, and that has to be, so h prime is this equivalent depth we are dealing with, and this is the depth of the motionless layer, which has to be much larger than this or the perturbations for it to be very weak, moving with basically immeasurable quantities. So this is mostly a valid assumption in the deep tropics, where this is what gives us the reduced gravity system. Okay, delta rho divided by rho. So here is rho plus delta rho is the deep layer. So delta rho divided by rho is going to be multiplied by g to give us the reduced gravity. It's forced with the wind stress at the surface, and that's going to create the perturbations to the interface, which are going to propagate the information in terms of waves, and those waves are going to interact with the background flow if there is a background flow. Okay, so starting with our zonal and meridional momentum equations and the continuity equation, you are now familiar with this. Again, h bar is the equivalent depth here. It cannot be too large because our assumption of h bar being much less than hd cannot be violated. So that's something to remember, as opposed to the atmosphere, which will be different. So write these now in terms of gh prime x g tilde, which is the reduced gravity, times h prime x. So we are going to replace these terms here with the reduced gravity, and we are going to ignore the u bar terms. So you just have du prime dt, this term, and this term, which is going to be balanced by wind forcing, which is spread on some depth scale d, minus mu u prime, which is the dissipation of the momentum with depth, or you can think of it as changes in h prime, which are compensated by entrainment. I don't know if you're already familiar with this process. When you do this convergence and deepening, or divergence and pulling up the interface, the turbulent kinetic energy of the wind stress can create entrainment of mass from below into the layer. Okay, So that depends on how the momentum is dissipated down in the active layer that we are looking at. Okay, if you don't understand it, wait till we get to the mixed layer processes, but there is that term mu u prime. Similarly in the meridional direction. Okay, so that's the meridional momentum equation, and this is our the mass continuity equation, which is related to, again, the dissipation, because entrainment is going to affect H prime and H. Okay, so ocean wave equations then. No background flow, so Py goes to 0 if you remember the coefficients. Qy is again this Coriolis and wave terms. To obtain an equivalent wave equation to 5.12, but for the ocean, we set the dissipation and entrainment to 0. So we are going to have mu term go to 0, and that means there is no exchange. So if water is converging somewhere in the upper layer, it has to diverge from somewhere. That's all. Okay, so eliminating u prime and h prime from these equations, so u prime and h prime are going to be eliminated again to write everything in terms of v prime, a single equation. So you do these manipulations, d dt of d squared v prime dx squared plus d prime d squared v prime dy squared plus beta dv prime dx minus 1 over c tilde squared. So we are writing the gravity wave speed in terms of the reduced gravity, and the third derivative of v prime and the Coriolis versus gravity wave speed of dv prime dt. So you can see here d dt of the divergence term in v prime and dv prime dt term, the acceleration term, equal to fxyt, where fxyt is this complicated looking thing which is related to wind stress, its variability in time, and its curl. So if the winds, if you have x and y like trade winds and westerlies, you remember we had a curl. So if your fingers are pointing towards the east and then west, so you're curling around the wind stress, the vorticity sign or the curl sign is downward negative z. So that's this term. Okay, so this is obviously function of xyt. This is the gravity wave speed, and we are seeking wave solutions in terms of v prime, tau x, and tau y. Okay, so tau here has a zonal and meridional wind stresses. So these can be then written in terms of, because of the coefficients being linear, we can write that in terms of vy and functions in x and y. X is a function of y, y is a function of y, times the waveform, which with equation 518 gives an equation for modes forced by varying wind stress. So this is 518, and we are going to reduce that to this harmonic equation or waveform. Okay, so it has d squared v dy squared term with this wave, and it's being forced by the wind stresses. Okay, ocean is very much a forced system at the surface, and friction is important because the wind stress is being putting momentum into the ocean with friction, and then whatever other assumptions you make in terms of entrainment and so on ride on top of that. So the free solution of this equation, if you set f equals 0, so free solutions means f equals 0, but this does not necessarily mean that wind stresses are 0. So you have a background state which you have set to 0. There is a wind burst and then the winds die away. That can set free waves into motion, as it happens with Kelvin waves and Rossby waves that we will see when we do El Nino and so on. So that gives this simple form. Well, simple form. So that looks similar to what we had done before, except that here the gravity wave speed and is replaced by the reduced gravity form, because you have the ocean being treated as an active layer on top of a quiescent deep layer. So that's our refraction squared, which looks like this in terms of the intrinsic dispersion, gravity wave speed, wave number, beta the Coriolis gradient, and so on. And the complication with respect to atmosphere, we have to really remember all the time for oceans, is that ocean has boundaries, so we will need boundary conditions, and waves do behave in a very nice, cute way in the ocean in terms of converting from equatorial Kelvin waves to coastal Kelvin waves, dispersing as Rossby waves, or Rossby waves hitting the western boundary, becoming short Rossby waves, and depositing energy to produce coastal Kelvin waves, and so on and so forth. So that is the general equation you want to remember, but then we want to convert that into specific cases like the upper ocean. The two important things there is this assumption of reduced gravity with ocean as a two-layer system and ocean boundaries. Okay? Simple in terms of when we get into physics, but the math of it is complicated, but we have to live through it, right?